This is a video from section 6.3 in linear algebra. Let R3 have the Euclidean inner product. Use the Gram-Schmidt process to transform the basis U1, U2, U3 into an orthonormal basis. Let's take a look at 29. U1 is the vector 1, 1, 1. U2 is the vector negative 1, 1, 0. And U3 is the vector 1, 2, 1. Notice, the inner product of U1 and U2 is equal to 1 times negative 1 plus 1 times 1, which is equal to 0. And so that tells me U1 and U2 are already orthogonal. But notice that U3 is not orthogonal to U2, and U3 is not orthogonal to U1. So we do still have a bit of work to do. Now, let's do the first step. V1 is equal to U1, which is equal to the vector 1, 1, 1. The norm of V1 is equal to the square root of 3. Second, if I want V2, to get V2, I take U2 minus the inner product of U2 and V1 divided by the norm of V1 squared, V1. But U2 dotted with V1 is equal to the vector negative 1, 1, 0 dotted with 1, 1, 1, which is equal to 0. And so therefore, the inner product of U2 and V1 is 0. And so what that tells me is that V2 is equal to U2, which is equal to negative 1, 1, 0. And so now, the norm of V2 is the square root of 2, and I will need that. Third, I want V3. So what we're doing right now is creating 3 orthogonal vectors. I want every pair to be orthogonal, every pair of vectors to be orthogonal to each other. Now, V3 is equal to U3 minus the inner product of U3 and V1 divided by the norm of V1 squared times V1 minus the inner product of U3 and V2 divided by the norm of V2 squared, V2. Come over to here. So U3 dotted with V1 is equal to 4. And so that told me that the inner product of U3 and V1 is 4. U3 dotted with V2 is equal to 1, and so the inner product of U3 and V2 is 1. Now we're set up to figure out V3. So V3 is the vector 1, 2, 1, and don't forget, let's go back. That's U3, right? 1, 2, 1. So I'm going to take the vector 1, 2, 1 minus 4/3 times the vector 1, 1, 1 minus 1/2 times the vector negative 1, 1, 0. Okay, so let's see if we can go back. Remember that the inner product of U3 and V1 is 4, right? And if we go back a little bit, the norm of V1 is the square root of 3. So the norm of V1 squared is the square root of 3 squared, which is equal to 3. So that's where I'm getting the 4/3 from. And then I'm multiplying by the vector 1, 1, 1. And I'm going to go minus. Now, the inner product of U3 and V2 is 1. That's where I get that number from. And then the norm of V2 squared is equal to 2. And then I'm multiplying by the vector negative 1, 1, 0. Now, if we simplify, I'm going to get 1 minus 4/3 plus 1/2 for the first component. I'm going to get 2 minus 4/3 minus 1/2 for the second, and then I'm going to get 1 minus 4/3 for the third component. And when we simplify, V3 ended up being the vector 1/6, 1/6, negative 1/3. Now, we need the norm of V3. The norm of V3 ended up being the square root of 6 divided by 6. Now, V1, V2, and V3 are my orthogonal set, right? Let me write that down. V1, V2, and V3, I claim, are orthogonal. But what am I looking for? I'm looking for an orthonormal set, which means every vector has to have a length of 1. And the way to do that is I need to take V1, start with V1. I'm going to divide every component by the norm of V1. And if we go back, the norm of V1 is the square root of 3. And then the norm of V2 ended up being the square root of 2. And then the norm of V3 is the square root of 6 over 6. So when I want my orthonormal set, I'm going to call Q1 my first vector. That'll be 1 over the square root of 3, 1 over the square root of 3, 1 over the square root of 3. That's the first vector. The second vector, Q2, is negative 1 over square root of 2, 1 over square root of 2, 0. My third vector, Q3, is 1 over the square root of 6, 1 over the square root of 6, negative 2 over the square root of 6. Is that okay? Because how did I get my first component? I took 1/6 and I divided by the square root of 6 over 6. The 6's cancel, and I get 1 over the square root of 6. And then basically I did the same thing. I took negative 1/3, I divided by square root of 6 over 6, and ended up with negative 2 over square root of 6. And so that's my Q3. So notice that Q1 and Q2 are orthogonal. Q2 and Q3 are orthogonal. And then Q1 and Q3 are orthogonal, right? And moreover, Q1, Q2, and Q3 all have norm 1, length 1. Okay, that'll do it for this video. This is a video from section 6.3, number 29. So I want you to be able to apply the Gram-Schmidt process. That's my goal for this section. So, thank you.